So I start our record, the usual thing. We still don't have that many participants. Let's wait just a little bit. In the meanwhile, what I want to show you is the calendar. Let me show you the calendar. Where is it? Here it is. Okay. Share. Wait, just 1 second. I want to make sure. Yes, share. Okay, now I can see that I'm sharing. Okay, so today we are going to finish with some of the things that are going to be in your final. So you're going to see some, where are we? Yes, Friday 29. Okay, so you're going to see some of this topic. And with today, essentially, we are going to finish what is going to be in the final. And then we are going to have next week another class. And I think that's it, only another class, where essentially we are going to cover some of the topics for your information, but they are not going to be in the final. Okay, let's start with the lectures. Okay, here we go. So last time we saw something about the specific heat. Just a reminder, Q is equal to M, the mass, C, which is the specific heat of it, and depends from each material. It has a different value. Remember, you normally find it on the table or provided in the problem. And then we have delta T, which is the difference in temperature. And delta T, just a remind, is always the final temperature minus the initial temperature. So when the temperature increase and you have delta T, which is positive, delta Q is also positive, and the energy flows into the system. It's positive because the mass is positive, C is always positive. So if delta T is positive, delta Q is positive and energy flowing into the system. While when the temperature decreases, delta T is negative, delta Q is negative, and the energy flows out of the system. We already say that when we have two objects that they have different temperature, like an ice cube outside of the fridge, so in contact with the air, in contact with the surface, what is going to happen is going to happen that the temperature is going to get the temperature of equilibrium. So the ice is going to increase the temperature, and the atmosphere right around the ice is going to decrease it, but then they're going to find a common point, okay? An equilibrium temperature. So let's review. We saw them last time, but we were a bit in a rush. So let's review some of the problem. We saw it last time. How much heat is needed to raise the temperature of aluminum by 5 degrees Celsius? This is a typical question that you might find in the final. So what you have, the mass is 0.5 kilogram. The temperature delta T is 5 degrees Celsius. So it is positive, right? We are providing the heat, we are providing heat to the system to raise the temperature. So of course it's positive here. And what is the specific heat of the aluminum is provided, which is 900 joules divided by kilogram C. So what is important is always that you check at the units. So here we have 0.5 kilograms. This is also provided in kilograms, so we are good to go. We don't need to make any unit changes. So we have the Q is equal to M, C of aluminum delta T, according to the formula we described it before. So I know mass, the mass is 0.5 kilogram, C aluminum is 900 joule divided by kilogram C, and then delta T is positive 5C because we are providing it to the system. So what we have is that Q is plus 2,250 joules, which is the energy, the heat that we are providing into the system. And also this is positive. So remember delta T and Q are always of the same sign. Very good. So very easy to do. Now, something a bit more complex. We have a 0.400 kilogram of aluminum tea kettle that contains 2 kilograms of water at 15 degrees Celsius. How much heat is required to raise the temperature of the water to 100 degrees? So here, you need to be careful because as you see, the problem is also providing the information about the aluminum kettle. So if there wouldn't be this information, it would be very easy and a problem exactly the same as the one we have seen before. But because here provides also the 400 kilogram aluminum tea kettle, you know that this is also need to be considered. So the heat, we need to raise the temperature, and is also say the temperature of the water and kettle. So he express it here. So you cannot just calculate only the one of the water. So when you are here, you have that the heat needed to raise the temperature of the water to T final is Q of the water is mass of the water, specific heat of water, delta T of water. So we have 2 kilograms, very good. C of the water is provided. So now it's not written here in the example, but if it is in the problem, it's going to be provided if in the final. So you're going to have these numbers with nobody is expecting you to know these numbers. So you get this number, you plug it here in the place of CW, and then you have delta T. Delta T is not 100C because this will be the T final. Delta T is T final minus T initial, because of course it changes, right? The temperature, if it was at 45 degrees, if it was at 90 degrees Celsius, the initial one, you don't need to provide that much heat. If it was at 0 heat, then you need to provide even more, right? So how much heat you need to provide depends on the initial temperature and on the final temperature. So that's why this is not T, is delta T. And so we have 100C minus 15. And so 2 kilograms multiplied by this, multiplied by 85 Celsius, and you find 712 kilojoule. If you end here, you have an answer to the problem, because the problem is says to raise the temperature of water and kettle. So we need also to see how much heat we need to provide to the kettle. The kettle is aluminum, so mass of aluminum, which is provided here, 0.400 kilogram, is already in kilogram, so no need to change anything. C of aluminum, which is going to be provided, and is this number here. Delta T of aluminum, again, 85 Celsius, because is not specified the temperature of the kettle, but we assume that they were in thermal equilibrium, so 15 degrees. So 85 degrees Celsius. You do the calculation and you find 30.6 kilojoules. So you see how, because the aluminum is a metal, how minimal is the heat that you need to provide the aluminum to get to 100 degrees with respect to the one that you need to provide to water. That's why the kettle is an aluminum, because you really don't need that much heat to make it get hot. And so we have that Q total is Q of the water plus Q of the aluminum the aluminum, and it's 742.6 kilojoules. So you sum up this with that. I don't know if there are, oh, this is okay. Reminders from Julia in the chat. But if you have any questions or you want me to go slower, let me know. So let's see another example, which might be even a bit more complicated. So this time we have a 0.010 kilogram, so the units are good, piece of unknown metal heated to 100 degrees Celsius and dropped into a bucket containing 0.5 kilogram of water at 20 degrees Celsius. So 100 degrees Celsius is like boiling water. So you know what I'm talking about. 20 degrees is, imagine that when your body is 36 degrees, so is half of the temperature of your body. So it's pretty chill, the type of chill that sometimes you need a light jacket, but not that much, but a light jacket. So just to give you an idea, right? So you have a piece of unknown metal heated at 100 degrees C, drop it into the bucket containing 0.5 kilogram of water at 20 degrees Celsius, like the ocean probably could be 20 degrees Celsius. Determine the specific heat of metal if the final temperature of the system is 50 Celsius. So as you see, the final temperature of the system is something in between, because you have the metal that is super hot and you put it into warm water, and what you get is 50 degrees Celsius, which is pretty hot, pretty hot. So you wouldn't be able to get into the water, it's a bit too hot. So what we use here, what is asking, determine the specific heat of the metal. So considering this final temperature, so it's a bit different. We need to find which metal is this. So we have the mass of the metal, we have the mass of the water, we have the specific heat of the water, we have the temperatures, the initial, the temperature for the first object, the initial temperature for the water, and the final temperature. So if we write the equation, what we need to consider is that the system is isolated. So the heat lost by the metal is the same as the heat acquired by the water. So the metal will lose heat, which means is going to be, Q is going to be negative, right? Because it's losing it. The water is going to get it, so it's going to be positive. And here we sum something positive with something that is going to be negative, and so the sum is going to be 0. So Q water plus Q metal is equal to 0. It makes sense because it's going to be positive plus something negative. So they need to be equal to 0. We need to solve this equation. So which one is Q of water? Q water is so small, tiny, and difficult to see. I'm hoping that you are able to see it at home. So what we have, let me enlarge it more for myself. Here is, we start with metal, sorry. So we have Q of the metal, mass of the metal, C of the metal, delta T of the metal, plus, and this is Q of the metal. The Q of the water, what is that? The mass of the water, C of the water, delta T of water. Okay, so let's start with the first one. The metal, we say that is 0.01 kilogram, the mass. C of the metal is what we are looking for, so we just leave it as a C. And then delta T. Delta T, remember, is always T final minus T initial. So we had 50C minus 100C, which indeed brings you something which is negative, because indeed we want this Q to be negative, right? So makes sense. And then what we have is instead all the information, the Q for the water. The water, we have 0.5 kilogram multiplied by C of the water, multiplied by what? T final minus T initial. T final is 50 C, T initial was 20 C. So the water is increasing its temperature, we are providing heat. So all this quantity here is going to be positive. If we do the calculation, we find minus 0.5 C of metal is plus this big number of joules equal to 0. So now to find C metal is very easy because I just need to divide by 0.5. Minus and minus goes away because I bring this in the other side of the equal. So minus goes away, is positive. If it's positive, it means that I've done everything correctly because C is supposed to be positive. And then I found this number and the units are joules kilogram per C. If we go to look in the table, we find that this C is the one of iron. So the unknown metal is iron. So a bit more complicated, but not even that much. We just need to remember that it's an isolated system. And because it is an isolated system, you have Q of the water plus Q of metal equal to 0. The heat is transferred from one object to another, doesn't get lost. Very good. Now, another one which was a bit more tricky. We have a 75 grams of cube of ice at minus 10 C. Minus 10 is very cold. So yeah, not even in winter. Yeah, in the mountains, up in the mountains, you find minus 10 C because otherwise it's more around 0 Celsius. So you have a 75 gram of cube of ice. So here already you see that we have grams. So here we will need to change it to kilograms because grams, we don't like grams with these equations. We like kilograms. Minus 10 C is placed in a 0.500 kilogram, these units, we like it, of water at 50 C in an insulating container so that no heat is lost to the environment. Very good. Will the ice melt completely? And what will be the final temperature of the system? So here, what is complicated in the reality is to understand the question because it's not asking for a specific quantity, it's asking for a more philosophical quantity, like will the ice melt completely? So what do? But you know that you have learned a couple of equations, so you certainly have to use this couple of equations. So at the end of the day, the heat required to completely melt the ice, how much it is? Q of the ice is the mass of the ice, C of the ice, delta T. Something that I haven't reviewed today, but we saw last time, is when I have a transition of phase from ice, for example, melting to water, every transition of phase, the temperature is no more involved. We say the temperature stays the same, doesn't change. What instead change is the phase of the object that before was water and now was ice and now is water. So we have mass of the ice, L. With this L, in this case, is LF, L of fusion. So these quantities will be provided to you. And this, when we provide these quantities, this is also an hint of which equations you need to use, right? So you're going to see here, C of the ice is such and such, LF, so which means the specific heat for fusion is such and such. So this should be a wake-up call and say, oh, then I need to use both of these equations. So what you have, Q of the ice is this, to make it to a temperature where it starts to melt. And after it gets to a temperature where it starts to melt, which we know at which temperature it starts to melt, then it has to melt. So the temperature is going to be the same. Okay, so let's see the Q of the ice is mass of the ice, which is 0.75 kilograms. I need to change this. If I leave 75, is going to get a completely different number. So you really need to do this thing. Multiply by the specific heat of ice, delta T. Delta T, now we know that for water, right, it starts to melt when you get to 0. So 0 is really the transition point. Below 0 is ice, above 0 is no more ice. So here you have final temperature is 0 minus initial temperature. The initial temperature is minus 10. Minus make it plus. And indeed, we are expecting this quantity here to be positive, right? Because we are providing heat to the system to raise its temperature. We said before, when I gave it, then it's positive. Q is positive. Is when I remove it, that Q is negative. So this quantity is positive. It makes sense. Okay, then let's go to the second one. The second one, we say when we are at 0 degrees Celsius, it starts to melt. So let's see, if I melt all the ice, what would I get? 0.075 kilogram multiplied by LF. This will be provided. And so you do your calculation and you find out that it's 27 kilojoule. Very good. Now, the heat required to cool the water to the freezing point is, let me see if there are there any questions on this part? I make it too big so I cannot see if there are. My screen is too big. I cannot see if there are questions. No? Okay, very good. So the heat required to cool the water to the freezing point, which one is this? Q of the water is the mass of the water, C of the water, delta T. Because the thing is, if the ice will not melt completely, then means that is the water that will become ice. So the mass of the water, C of the water, delta T of the water, or at least will be the water which will decrease to the icing temperature. So here what we have is 0.5 kilogram multiplied by C of the water, which is this one, delta T. Delta T is T initial minus T final. Okay, so in this case, we have 50 degrees minus 0, because it will be to 0 the temperature, which means under, if I do all the calculation, is 105 kilojoules. So since the temperature of the ice is way smaller than, not the temperature, sorry, the heat that I need to provide to the ice to be melted is way smaller to the heat of the water, so the ice will completely melt. Okay. Because you see, it takes very minimum amount of this to melt the ice with respect to the heat that you will need to provide to the water. What will be the final temperature of the system? So to find the final temperature of the system, no heat is lost to the environment. So the heat lost by the water is gained by the ice. So what we have is that Q ice plus Q water is equal to 0. So here you need to pay attention. So mass of the ice, C of the ice, delta T, which is the one that we have seen before, to make the temperature increase from minus 10 to 0. Then what I have, once in 0, I have the mass of the ice and the fusion, the specific heat for fusion. So the ice is becoming water, and this is the heat to make the ice melting into water. Then what we have? We have, let's look at the last equation. The water, which will decrease the temperature to the final temperature. So we are going to have the water, which is going to decrease the temperature to the final temperature. And this is the thing. And then here, what we are going to have, and this is the important piece, we are going to have the ice that after it's melted, and so it's water. So that's why the mass is the mass of the ice, but C is the specific heat of water, will go from the 0 temperature to the final temperature, right? So once the ice is melted, of course, it becomes water. And so it's an additional mass, if you want, is an additional mass that goes into the mass of the water. What we could have done, indeed, is to remove this part of the equation and simply leave this one, considering that now the mass is no more the mass of the initial mass of the water. Now the mass of the water is the mass of the water and the mass of the ice. But no, what I actually said is a mistake. Because why it is a mistake? What I actually said right now is a mistake, because the initial temperature of the water is different from the initial temperature of the mass that just become water, of the ice that just become water. So this is all related to the water. So this is the information of before, 0.5 kilograms, and then you have the C of the water, which is this one, and then you have your 50 Celsius as initial temperature, right? 65 as initial temperature. Here instead, T final is the one that we are looking for. This object here instead, the mass of the ice, we have it, is this one, 0.075 kilogram. Now we have C of the water, because the ice has been all, it become all water. And then we have T final minus T initial. T initial is the temperature of the ice, which was 0. To melt, the ice had to be at 0, right? So this is the initial temperature of the ice. Very good. When it melted to water. So what we do is mass of the ice, C of the ice, delta T, mass of the ice, LF, and then here I put together mass of the ice, mass of the water, then multiply C of the water, T final, minus mass of the water, C water, T initial. So I know everything of this number, essentially, but T final. So once I substitute everything and I do the calculation, I found that T final is equal to 32.4 Celsius. So this was the tricky one that I wanted to review with you. Okay, then let's see another problem that we haven't seen, and this is more typical what you are going to find in the finals. Compute the heat of fusion of a substance from this data. 31.15 kilojoule will change 0.500 kilogram of the solid at 21 Celsius to liquid at 327 Celsius, the melting point. The specific heat of a solid is 0.129 kilojoules divided by kilogram Kelvin. Okay, this time we have Kelvin. So here what we have, we can use the conservation of energy. All the energy went to heat up and melt the substance. So all the heat, Q, is mc delta T plus mLF. I'm looking for what? The specific LF is the one that I'm looking for, the heat fusion. I'm looking for the heat fusion of a substance. LF is what I'm looking for. So this is equal to Q minus MC delta T divided by M. And now I know all this information. So I have here 31.15 kilojoule minus 0.500 kilogram multiplied by what? The specific heat, which is this one. Specific heat is indicated here, and delta T, which is 327 minus 21, 306 Kelvin. Although here is, because with delta T, you can use it. You don't need to change it. Remember, also Mike said the other time, if you have Celsius or delta T for Celsius or delta T for Kelvin are the same. So you don't actually need to convert 21C in Kelvin, 327 in Kelvin, and then do delta T. You can just do delta T because like this, because they are the same. And so we just write 306 Kelvin. We do all the calculation and we found 22.8. Very good. So now I want to show you some information about the heat transfer. From this part, we do not require that you know any formula. So it's just more qualitatively that you need to understand. So heat can be transferred via three methods: conduction, convection, and radiation. So conduction is the transfer of heat through a substance. If the cup that holds your hot coffee is a good conductor of heat, you will need a sleeve to keep from burning your hand. And so typically, which are very good conductors, they are metal, because they have electrons that are very free to move through the material, while non-metals are not. So I think you have done the atoms. So some of the atoms, you've seen that they have in chemistry, some of the atoms you've seen that they have the electrons that are more easily to move around. So in this case, metals, heavy elements, and electrons are easy to move around, and so they can really transfer heat very easily. So the transfer can be viewed as an atomic scale. It's an exchange of energy between microscopic particles by collision. Less energetic particles gain energy during the collision with more energetic particles. The rate of conduction depends upon the characteristics, of course, of the substance. Then we have conduction, the slab, Then still for the conduction, the slabs allow energy to transfer from the region of higher temperature to the region at lower temperature. Here we have a higher temperature, here we have a lower temperature, and the heat flows. It flows with the pressure that is Q divided by T. And where we have a thermal conductivity, the area of the slab, the delta T, T final minus T of the hot minus T that is colder, delta X. And so these represent the pressure, the heat flow, how fast the heat flows. And A is, so the cross-sectional area, delta X is the thickness of the slab or the length of a rod, and P is in watts because it's a pressure, and then Q is in joules, and T is in seconds. So K is called thermal conductivity of the material. So good conductors have high K values, while good insulator have low K values. And here we have some examples of values, and you can see that for metals, they all have a very high value of K, of the thermal conductivity. So 200, 390, oh yeah, Mike is back, very good. Silver is 420, while you instead see, for example, for example, water is 0.57. And indeed, we see before in the example of the kettle with water, how much heat was necessary to heat the kettle, very little. We compare to the water, which instead needed much more heat, right? So the aluminum is a good conductor while water is not that good. Then we have gas. Gas are even worse conductors. And so we have air is 0.024, for example, with respect to aluminum, which is 240. So yeah, these are the thermal conductivity for yeah, metal, liquids, gases, and other solids.
This is something that I mean, everyone kind of knows this already, that the reason a blanket keeps you warm is because, you know, fabrics like cotton, and then all of the air gaps, right, that are contained inside of it, right? And this is why your clothing and your hair keep you warm, is because the air gaps and the fabric itself have very low thermal conductivity. So it takes a long time for either your body heat to work its way through and get out, or I don't know, if you want to think about it the other way around, for the cold to get in, right? So
yes.
yeah. So whereas metals, this is important to know, like when you take, you know, a big metal cookie sheet out of the oven, it's going to cool very quickly, not only because it has a low specific heat, but because it's also highly thermally conductive. And that's one of the reasons why, you know, copper pans are more expensive than steel pans, because the copper is more conductive. It heats more evenly, even when the heat's applied only at one place. Yeah, but the food itself will stay hot much longer. And that's a combination, like, you know, when you have cookies or roasts or whatever, and you pull them out of the oven, then partly it's because the high specific heat capacity, but partly because their conductivity is so low as well.
Very good. And yeah, also when insulating a house, for example, we want material whose thermal conductivity is as low as possible, you know, so that we can keep it more warmer. Then the heat transfers in fluid is mostly instead by convection, which is the result of mass transfer. So the heat is transferred as warmer fluid moves to replace cooler fluids. So convection might be spontaneous or forced. For example, here we have during the day, we see that the sea breeze arrive here. Here we have the air current with the sun that it makes it warmer. And then it's circulated like this, right? The warmer temperature goes up, and then when it goes up, it gets cooler. And then when it gets cooler, it comes down. And then when it comes down and it gets more closer to Earth, closer to the land, because the land is warmer than the water, it makes warmer, and so on. So you have this movement, this circular movement, that is what make the heat transfer. And this is also used for the heater, that they force hot air. And so, for example, here we have furnace, okay? So we have hot air that's coming here, and then the more it goes away from the source of heat, the more it becomes cooler. And when it's cooler here, it goes down again, and it gets again inside here, and in this circle we have the heat transfer. I don't know if you want to add something.
I'll just say that nature will cause natural convection, right? The spontaneous convection, because it's just a much faster way to get energy or heat from one place in a gas or liquid to another. We saw how low the thermal conductivities of gases and liquids are. So if you wait for the gas or liquid molecules to jiggle their neighbors and jiggle their neighbors, it just takes, you know, it takes very long time to do that. And so what will happen instead is the fluid will just spontaneously cause those convection cycles on its own. Yep.
Yeah.
Nature wants to try to even out temperature differences, right? It's sort of like driven by that.
Yeah. So the energy is transferred by the movement of the substance. And when the movement results from difference in density, then it's called natural convection. And when the movement instead is forced by a fan or a pump, then it's called forced convection. And this is the rate of transport by convection. P is H A delta T, where H is the coefficient of convection, A is the surface area, and then delta T is the difference between the surface and the convecting fluid. Then we have radiation, which is the only type of heat transfer that can take place through a vacuum. So you can feel the radiation of it when you stand near a fireplace. And this radiation is the form of electromagnetic waves and in the infrared part of the spectrum. So the radiation does not require physical contact. All objects radiate energy continuously in the form of electromagnetic waves due to thermal vibration of their molecules. And so they emit electromagnetic radiation. For example, the perfect absorber and emitter in electromagnetic is called the black body. And the radiation is given by Stephen Law's equation, which is P is equal to sigma A T to the 4, where A is the surface area of the emitting body, T is the temperature, and sigma is this value indicated here, and is called the Stephen-Boltzmann constant. This, for example, you really use it in astronomy because, of course, then there is vacuum, right? And also because the black body, a star is considered like a perfect black body. So if you become an astronomer, this equation is really, really important to you. Example, the electromagnetic waves carry the energy from the fire to the ends, and you don't have any physical contact that is necessary to transfer the radiation. Here again is the equation of the Stephen-Boltzmann law is written again. And in this case, we have E also, which is a constant called the emissivity and varies from 0 to 10. 0 is for a perfect reflector and 1 is for a black body. And the temperature here is always indicated in kelvins. So I don't know, Mike, if you want to add a few things. But...
I'll just add the comment that for Physics 151 and for our current problem set in the final exam, we do want you to know qualitatively what these 3 different modes of energy transport are. But you won't need to use these equations to do numerical calculations for us. Thanks.
Yes, very good. I said it, but it's good that you repeat it because we don't want to scare them. So here, for example, we have a spectrum that shows the amount of radiation emitted at a particular wavelength. So for the black body, the peak of the spectrum is determined only by its temperature. So this is really important to understand. Sorry, I have my phone here. Somebody's calling me. So we have all these, the Stephen-Boltzmann equation that we wrote before is essentially can be expressed in this way with this radiation, which is with the wavelength, which is the Wien's law. Lambda max, T max is equal to this value. So when we see that the radiation provided by a body, it only depends on the temperature. And this is also used, right, Mike, in astronomy to find the temperature of particular object in the sky. Because you see
very much. Yeah. And this one equation I come back to in Physics 152 when I teach Physics 152. So I don't know if Dr. Rubin will, but yeah. And by the way, when we talk about a black body here, you can imagine a glowing charcoal, you know, in a fireplace or in a barbecue, or you can imagine maybe molten lava. All these things are glowing just because they're hot. And this is what we're talking about. We're talking about the sort of power or amount of energy given off in light, in the form of light, as a function of the color of the light, right? So when an object is only 1500 kelvins, which would be like lava, right? I think lava is around 1500 kelvins. right? When it's up on the surface of the earth, right? When just sort of flowing, then it's giving off some visible light, but it's giving off a lot of infrared light. And the most common color of the light it's giving off is at 1.5 micrometers, which is in the infrared. So your eye can't see that. Your eye can only see this part right here of the visible light that it gives off. And then if you heat it hotter, like a molten metal is like 2000 kelvins, and then you can see a lot more of the glowing visible light coming off of it. If you've ever seen it in movies or on television, right? Like molten metal. Thanks.
Nice. Thank you. So with the surrounding, the rate at which the object at the temperature T with the surroundings at T naught radiates, of course, is, but maybe this you don't even need because we don't want you to study too much this equation. So don't worry about that. So for an ideal absorber is defined as an object that absorbs all the energy incident on it. So this is an ideal absorber, while an ideal refractor, and so the type of object which is called, which we call black body, is an ideal absorber and is also an ideal radiator of energy. So an ideal reflector absorbs none of the energy incident on it. Okay, so this is ideal absorber, ideal reflector, and this is black body. Ideal absorber and also ideal radiator of energy. This we don't need to see this example because you are not going to use this. And then we have what is called thermal expansion. So the thermal expansion of an object is a consequence of the change in the average separation between its constituent atoms or molecules. And at ordinary temperature, molecules vibrate with a small amplitude. And as temperature increases, the amplitude increases. And this causes the overall object as a whole to expand. And probably you have seen this with the, if you use the, also, for example, the glass, when you want to make the glass, so you have to blow it inside after you put it very, very hot. And so you can change the shape and expand when you're making glass. And also, for example, also with the metals, if I need to open if I need to open a jar with something inside and it's very, very strong, sometimes what you do is just to eat the top. Then you need to be careful because it's going to be very heat. So you need to use something to open it. But what is going to happen is that the metal is going to expand. And so because it expands, it's easier to open the top of a jar. And so how it goes this with the formula for most changes in temperature, which have the delta L is equal to alpha L naught delta T. So where alpha is considered the coefficient of linear expansion, delta T, yes, this T is capital T because it's a temperature in the reality. It's indicated small, but it's the temperature. And alpha depends on the material. When we have a linear expansion in 2 dimensions, then we have delta A, sorry, which is gamma A naught delta T. And gamma is going to be equal to 2 alpha. When we have 3-dimensional, we have that delta V, so the new, how it changes the V final with respect to V initial is beta V naught delta T for the solids, where beta is equal to 3 alpha. So delta L means how much L final dimension, final length minus initial length is equal to alpha initial length delta T. Delta A is final area minus initial area, which is gamma A initial delta T, and gamma we already seen is 2 times alpha. And delta V instead is final volume minus initial volume, which is beta initial volume, delta T, and beta is 3 times alpha. And with this thing, I think we have finished our classes and we have finished all the material that is covered in the final. So next class will be a conclusion of the thermodynamic course, and but there will be concepts that you are not going to find in the final. So we are going to cover them because we want you to know everything about it, but it's not going to be in the final. Mike, do you want to add something for the
Right.
students?
Nope, that's it. That's it exactly. So up to right here to thermal expansion, this is what's on the current problem set, and that's what will be on the final exam. This is all in chapter 14 of our textbook. Yep. And then on Monday's lecture will be some of the chapter 15, 16 material, what we called lectures 28 to 30, but that is all optional, won't be on the final exam. Won't be on any problem sets.
Okay.
Thank you.
Sounds good. So is going to be next class, our last class, right?
I think so. I think Monday's lecture is the final Zoom lecture.
Yes.
That's right.
Very good.
Julia is going to be on Zoom here for the next hour. And then after that, Ewan. So if you have any questions about the current problem set, please stick around or come back later today.
Bye-bye. Bye, everyone. Happy Friday.